The sea. To man, it is a highway, a battlefield, an endless source of food, a challenge to his skill and imagination. For thousands of years, man has known the sea, lived on it, by its shores. He has seen it from land, from the deck of a ship, from an aircraft a few thousand feet above the surface. He has monitored its temperatures, checked its currents, explored its depths. He fears the sea for its storms, its vastness, its hidden mysteries. But because of his proximity, he has never been able to observe the magnitude of this restless, changing mass. Now, however, he has gone to outer space. Now he can look at the sea with a new perspective. Now he has a chance to increase his understanding of inner space. To scientists of all disciplines, Skylab is an exciting new tool, providing them with a wealth of data that will supply them for years. From high above the Earth, phenomena that can be observed firsthand, phenomena previously known only in theory, solid information that substantiates what is seen from the limited view on Earth and tells us of new resource waiting to be discovered. The rich product of two previous Skylabs have inspired scientists to ask even more questions. And now, on Skylab 4, these specific areas of interest receive full attention. One of many missions set forth for this crew. Marine Colonel Gerald Carr, Air Force Colonel William Pogue, Dr. Edward Gibson, solar physicist, is to photograph the sea, its currents, its boundaries, its turbulence. 6 cameras in Skylab's multispectral facility allow the crew to widen the scope of material. The cameras alone cannot capture the subtle differences in color and texture that man's eye can see. Through the eyes of the crew and their cameras, we see storms on the sea, discover promising fishing grounds, find surface hotspots that hint of new energy sources, learn there may be water beneath Africa's parched earth, watch the comet Kahutek thread through the skies. And the view from the wardroom window frequently is more eloquent than that brought back on film. Although the crew has taken a cram course in oceanography, their observations are restricted to accurate descriptions and remarkable photography.
Okay, what I'm going to try to do today is show you a little bit about what we know about the Falkland Current and what we hope to look at today. We hope to have a couple of opportunities to see the Falkland Current and to see some of the plankton blooming that indicates to us that the current is there. And we're going to especially look at the confluence of the Falkland Currents and the South Equatorial Currents as they come together just to the east and southeast of Buenos Aires and Montevideo. Now this is what our orbit is going to look like. We're going to have two opportunities to look at this area. The first pass, we're going to be coming down through here. We'll cross the southern tip of South America, and our side angle, our look angle, is going to be off to the south, southeast in this area here. So we expect to be able to see the Cape Horn area, the Straits of Magellan, the Falkland Islands, and the currents. Now our next pass, which will be about an hour and 3/4 later, will follow this route right here, and we'll come up a little more inland, and we'll be looking out in this direction again, looking to the southeast. So you see we're going to have two whacks at it. We'll look at it once here and once here. Now let me show you in a little more detail just what it is we're interested in here. Of primary interest for our observations today is the Falkland Current. And this is the Falkland Current right here. Now what we have is the west wind drift. We have this very slow current that moves well down in the south of the southern tip of South America. Now these again are the Falkland Islands. Here's the Straits of Magellan. Our first run is going to be up this way. We'll be able to see this area out here. Our next run will be more up in this direction, and we should be able to see out in this area where we have the confluence. Now here we have the South Equatorial Current. Now it's rotating in this direction up north of this area. We have the west wind drift this way, and you have this little area here, this current, where the west wind drift area is trapped in this narrowing area here called the Falkland Current, these being the Falkland Islands. Okay, the next thing you'll be seeing will be observations out the S-190 window, which is the Earth Resources window that looks straight down. Okay, as we come up the eastern coast of South America, you can see it's getting pretty cloudy. Way down there in the center of your screen is the southernmost tip of South America and the Straits of Magellan. Okay. Now, as we move up here into this area of cloud, there's a few patches through which we can see some of the green, light green blooming of the Falkland Current. Now, you can see the current now going from the center of the screen out to about the 9 o'clock position. I'm going to reach around and stick my finger in front of the lens or a pencil. I don't know if it's going to be focused well enough to show it to you. But right there is the Falkland Current. See that chlorophyll blooming? Now what we're seeing is the current as it moves in toward the Falkland Islands. All along this area here, we can see the plankton blooming very, very clearly. The plankton is a nice light yellow, sort of an aquamarine color. Not light yellow, I mean light green, more of an aquamarine color. The South Equatorial Current, on the other hand, seems to be a little darker green. The ocean itself in this area is a nice deep blue color.
December 6, 1973. A significant day in oceanography as Skylab passes over the Caribbean. The crew is asked to observe and photograph the Yucatan Current. A scientist from the Office of Naval Research has recognized cold core eddies in photos from Skylab 2.
Skylab Houston, we're about 30 seconds from LOS. We'll call you at the Vanguard at 1547.
Roger, Dick. We think we see the phenomena that was mentioned in the message. We do see the cloud streaks with the arcs of cumulus overlaid. There are some differences in color of the water surface underneath, running from dark blue to light to the green. There's no sun glint, however, to help us out.
Roger, Jerry. Thank you.
We've grabbed a few Nikon 55mm pictures of it.
Okay.
Do you see any eddies? They are asked. Visible to the east is a large flat surface with smoother waters than the surrounding ocean. The first cold core eddy ever recognized by man from space. Above it float towering crescent-shaped cumulus clouds. The Yucatan Current, which spawns this core of cold water, flows north. Above it are cloud streets. The combination of cold water embedded in warm currents creates the atmospheric manifestation of the crescent-shaped clouds. The eddies are created from the regular orderly turbulence along the boundary of the current. They form wherever the current changes in velocity, causing shearing. As the eddies move downstream, they merge or coalesce with other eddies, grow larger. The eddy seen in the Caribbean was estimated at 35 to 40 miles in diameter. Although such eddies have been created in test tanks in the laboratory, Skylab has given us the first opportunity to actually see this phenomenon in the ocean. On January 24, 1974, a Navy weather plane left Jacksonville, Florida, to confirm what the astronauts had seen. The plane followed Skylab's flight line, dropping 2 lines of air-expendable bathythermographs, AXBTs, 1 every 10 miles for 200 miles. Temperature profiles indicated that shearing constantly was taking place along the powerful Yucatan Current, resulting in cold core eddies. Another eddy was spotted in the Strait of Gibraltar. There, warm and cold water meeting have caused an ocean front, clearly defined in this view. Surface slicks indicate the direction of the current, which flows swiftly through the strait. Cold water eddies have formed in the Mediterranean. Cold core ocean eddies form along the left-hand side of any major current in the northern hemisphere, along the right-hand side of those in the southern hemisphere. Another photo shows a well-defined ocean front off Kangaroo Island. The long line of swells is absorbed as it hits the boundary current. Ocean upwelling in the New Zealand current could influence fishing grounds. In this view, huge blooms of plankton, the bread of the sea, are seen spreading for 500 miles in the current. This photograph also shows wind streaks and another ocean front. In previous Skylabs, cameras were not sensitive enough to pick up signs of turbulence moving downstream behind a blunt island. A ship wake about 15 miles long can be seen quite clearly. The study of ocean currents, turbulence, and cold core eddies is to continue with the Apollo-Soyuz test project in 1975. The United States capsule will mate with that of the Soviet Union 100 miles above the Earth. Fewer orbits, and therefore fewer opportunities for research, will be possible due to the lower altitude. But an ambitious program still is planned. As our American crew works with the Russians on this mission, United States Navy ships will back up new discoveries with data collection at sea. On the ocean's surface, they will use equipment to monitor currents, temperature, and weather, while the test project orbits overhead. Areas of interest include the Western Caribbean, the Coral Sea, Indian Ocean, southeast Brazilian coast, and the Strait of Gibraltar. A major study will involve the Japanese current. Here, for the first time, we may be able to watch the growth of an eddy, which could increase unchecked for 1,000 miles. Much of this study will be funded by the Office of Naval Research, making the United States Navy a world leader in the determination of orderly turbulent formation in the ocean. The success of this mission will rely heavily on the cooperation between scientists, the surface Navy, and our astronauts. Through the eyes of our men in space, we now have the capability to provide real-time information on turbulence in the world's oceans. Someday, when we know more, such information could be relayed by satellite. To a tactical commander, such real-time information about ocean boundaries and cold water eddies could be invaluable. He needs to know how the ocean will affect his sonar, his ASW, and submarine forces, both to find his enemy and to protect himself. From ship, aircraft, and land, man has seen blue water and waves. Through oceanographic studies, he has learned that there are boundaries and breaks in the ocean, but now he has seen them from space. Skylab, now orbiting empty in space, was a unique new tool with which to help us understand the ocean. But the key to our understanding still is man. Whether he flies high above the earth, operating the finest equipment devised, or waits patiently on the swelling ocean, planting monitors and listening to the sounds of the sea, only his eyes, his brain, and his ability to interpret will one day unlock the door to our greatest natural resource, the sea.